Hello everyone, it's a great pleasure to introduce an oral presentation on the ninth International Conference of Material Science and Technology. My name is Vladimir Safin and come from Russia. Our presentation, named Anisotropic Needle Coke based on cold dissolved products, was prepared in collaboration between Russian and Mongolian Institution of Chemistry and Chemical Technology and with the participation of Shandong University, China. You can see information about foundation on the slide. Modern environmental protection requirements are driving a gradual transformation of the carbon industry's feedstock base. Numerous studies have focused on identifying alternative precursors. Such materials must contain minimal level of carcinogens, notably benzoypyrene. Additionally, this alternative feedstock should primarily consist of polycyclic aromatic compounds, which are critical for production of carbon materials with high anisotropy. Our previous work showed that mild cold dissolution in highly boiling technical hydrocarbon fractions, such as coal tar, its interesting fraction, or heavy cyclic oil, allows to produce a coal extract. They consist of polyaromatic hydrocarbons and can be used as an alternative coal binder material. This study is related to production of another valuable material, namely needle coke, which demonstrates superior properties including low thermal expansion coefficient, high electricity conductivity, extraordinary mechanical strength, and so on. This study focused on the composition of different fractions isolated from the coal extracts obtained by dissolution of coal in various technical solvents, as well as the structure of the coke formed from them. The aim of the study is to investigate how the composition of the fractions affects the surface morphology and crystalline structure of resulting coke. The initial sample for the thermal dissolution was a bituminous coal from Chadan deposits of the Ulukhem coal basin. We used an autoclave equipment depicted on figure 3 for coal extracts obtaining via coal dissolution process. The coal was grounded previously to finest of less than 0.2 millimeters and mixed with the solvents to form a paste in a ratio of 1/3 coal to 2/3 solvent by weight. Coal tar, anthracene fraction of coal tar, heavy pyrolysis tar, heavy cyclic oil from catalytic cracker unit, and a mixture of coal tar and heavy catalytic oil in 50-50 ratio by weight were applied as solvent for the coal. After preparing the paste, we placed to autoclave and heat at 380 degrees Celsius for 1 hour under aftergenous pressure. As a result, we received coal extracts and not more than 5% of gases and liquid products. Our previous investigations showed that under the conditions applied, coal dissolutions can be considered a radical reaction that proceed primarily through thermally activated solvolysis, depolymerization at the weakest linkage, such as ether or methylene bridge between polyaromatic units, rather than as a non-selective thermal radical destruction with subsequent solubilization of the resulting molecules fragments. The sixth slide presents a scheme of the conducted research. After the reaction, the obtained extract were subjected to separation. Extraction and distillation process were employed for this purpose. Distillates with boiling point from 230 to 450 degrees Celsius and substances soluble in or insoluble in toluene serve as feedstock for further carbonization. Some samples were purified by selective removal of carboxylic acid, phenols, and organic bases. The resulting coke was obtained in two stages. The first stage was carried out at temperature of 475 degrees Celsius for 5 hours of soaking time. The reaction pressure was maintained at approximately 0.8 megapascal, and excess pressure was released through a control valve. The first stage carbonization products, named semi-coke, were subjected to higher temperature coking in chemical crucible with ground leads in a muffle furnace under the inert atmosphere at 1100 for 1 hour. All obtained products, such as various fractions, semi-cokes, and calcinated cokes, were investigated by multiple methods, including GCMC, Fourier transformed infrared spectroscopy, and nuclear magnetic resonance spectroscopy. According to elementary analysis, is shown in table 1, the fractional comprise up to 88.8% of carbon. The hydrogen content is higher in distillate fraction from coal extracts in coal tar and in the mixture of coal tar and heavy cyclic oil. Extraction of phenols, acid, and organic bases resulted in a decrease in nitrogen and oxygen content by only 25-27%. This indicates that most of these heteroatoms are found in natural H-cycle oxygen and nitrogen containing compounds. Fourier transformation infrared spectra indicates the dominance of aromatic compounds through absorption band in the spectral region of 3000 to 3100 wave numbers. The most characteristic absorption bands between 2800 and 3100 waves number were deconvoluted, and semi-quantitative molecular indexes of hydrogen aromaticity and carbon aromaticity were estimated based on the deconvoluted spectra. The nuclear magnetic resonance spectra show strong signals in the spectral region of 9.5 to 6.7 ppm related to aromatic protons and weak signals from aliphatic protons. The molecular indices estimated from Fourier transformed infrared spectroscopy and nuclear magnetic resonance spectra are shown in table 7. The data confirmed that all fractions consist predominantly of aromatic compounds. Distillate fraction from coal extracts in coal tar and anthracene fraction of coal tar exhibit higher carbon and hydrogen aromaticity and a lower degree of aromatic ring substitution. Other fractions are characterized by relative low aromaticity and can be seen from the CR, HR, and FR indices, and by a higher degree of aromatic ring substitution. The ninth slide shows a scheme of distillate fraction purification in figure 8 and obtain results. The group composition of distillate fractions on the type of solvent used for coal dissolution. Distillate fractions from coal extracts in heavy pyrolytic tar contain more oxygen-containing compound, namely phenols and carboxylic acid. The main polar substances in distillate fractions from the coal extracts in coal tar and anthracene fraction of coal tar are organic bases. We believe that the organic basis fraction includes compounds such as pyridine, acridine, and quinoline derivatives, which are typical for coal processing products. Gas chromatography mass spectroscopy was used to study the molecular composition of the natural fraction obtained from distillate fractions. We used a combination of polar and non-polar column, which work well for mixture consist of condensed aphthenic aromatic compounds. We identified between 391 and 558 organic compounds in the samples. The main components were various aromatic hydrocarbons with 2 to 4 condensate rings and hybrid hydrocarbons. As summarized in table 5, the main components of polyaromatic hydrocarbons are anthracene, phenantine, and pyrene derivatives. The content of crusenethene derivatives is very low. Polyaromatic hydrocarbons in distillate fractions are present in both substitution and unsubstitution forms. Substitution polyaromatic compounds had 1 to 3 methyl substances per molecule. On average, the substances were no longer than 2 carbon atoms. This is confirmed by the nuclear magnetic resonance spectroscopy result. The analysis of optical images displayed on figure 10 revealed that coke samples to exhibit an anisotropy depending on type of distillate fraction used. Pay attention to figure 9, A and H. Coking of the distillate fraction obtained from coal extracts in the anthracene fraction, which consisted predominantly of tricyclic aromatic components, result in poorly developed anisotropy with rather short fibers. Similarly, the toluene insoluble fractions gave isotropic coke. Coke samples depicted in figure 10, C, D, and G, obtained by coking of fractions from coal extract in mixture of coal tar and heavy cyclic oil, and heavy pyrolytic tar exhibit more developed anisotropy texture with fiber of 900 millimeters and average scope of 5.4 to 5.8. The average texture score for the coke obtained from the refined distillate fractions increased to 5.8 to 6.6, and it can be seen from figure 10, C and F. The increase in anisotropy as a result of purification was achieved through the development of higher scoring texture. XRD patterns of the coke are shown in figure 11. All the samples are characterized by white diffraction reflection typical of carbon material containing disordered structures. The most intense asymmetric peak with a maximum at 2 phi around 26 degrees corresponds to the reflection from the 002 plane of graphite-like structures. Weak white reflections from the 100, 004, and 110 planes are also observed in other regions. From the deconvolution of the 002 peak, 4 structural components were identified. Graphitic domains are formed by an ordering packing of flat polymerscience layers, like graphenes. Domains with a turbostatic packing are characterized by a less regular structure. Based on the convoluted XRD patterns, the proportion of the structural components and the crystalline parameters were calculated and shown in figure 11. Figure 12 shows that coke samples consist predominantly of turbostatic and graphitic crystallite domains. The proportion of disordered gamma 1 component did not exceed 24%, and that of the gamma 2 components was no more than 2%. Similarly to the coke microstructure, the content of structural components depends on the composition of the distillate fraction used. Table 6 represents the parameter of crystalline structure of cokes. The samples obtained from the coal extracts in heavy pyrolysis tar is close to graphite in terms of interplanar distance. A comparison of optical microstructure results and XRD data shows that a general trend is observed between the degree of graphitization and coke anisotropy. The higher the proportion of graphite domains, the more anisotropic the coke. Correlation analysis was performed to reveal the effect of distillate fraction composition on the crystalline structure and texture of obtained cokes. The parameters tested include the content of the main organic molecules, the concentration of polar substances, and the abundance of substitute and unsubstituted polyaromatic hydrocarbons in the fractions. Based on the result, we identified 2 main factors that influenced the coke structure. Firstly, the structure of polyaromatic hydrocarbons affect the coke structure. The effect of substituted and unsubstituted tri- and tetraaromatic components is shown in figure 14. Unsubstituted tri- and tetraaromatic components is the effect on graphitization. In contrast, alkyl substituted tetracyclic aromatic promote graphitization and anisotropy. The correlation between aromatic ring substitution determined from nuclear magnetic resonance spectra and the proportion of graphite domains proves this conclusion. This is because polyaromatic compounds are rather thermally stable during delayed cooking and act as a mesogens during mesophase formation. Due to the presence of active hydrogen, they can, along with naphthenic and naphtheno-aromatic hydrocarbons, control the course of radical reaction by stabilizing radicals with hydrogen, thereby preventing premature coke production. Also, their alkyl substituent as well as aliphatic components may gradually decompose into gaseous products. The latter create a gas flow that act a driving force for initial arrangement of the flow structure of the mobile bulk mesophase. The second factor is related to purification. The obtained data demonstrate that the proportion of graphite domains obtained from distillate fractions free of polar components increasing by 6 to 8 comprised with the original depths. The effect results from the removal of phenol carboxylic acid and organic bases, which are highly reactive in condensation and polymerization of aromatic feedstock molecules into char and which hinder the planar orientation and stacking of polyaromatic clusters. The conclusion present on slide 15. Thank you for your attention. Goodbye.